Om Shri Sai Ram. Dear students, welcome to this third lecture on the topic of motion. So, before we proceed, let us see what we have discussed so far. So, we have started our discussion with the parameters of distance and displacement. We have defined what is distance, what is displacement, how do we define them, what are the formulas, what are their SI units, and also we knew what is the exact difference between these two. So, though this distance and displacement have the same SI unit, they differ by some quantity, and the quantity which separates both of them is the direction. So, distance is independent of direction, but the same distance when we specify with direction we call it displacement. Now, from this, when we take the rate of change of distance or rate of change of displacement, which means what? Rate of change is change with respect to time. So, rate of change, we have seen that rate of change of any physical parameters is same as the change of that parameter with respect to time. So, rate of change of distance is speed, that is change in distance by time. Similarly, rate of change of displacement is called velocity. Now, whatever difference is there between distance and displacement, the same difference we see between speed and velocity. After having defined what is speed, what is velocity, after having discussed the formula and SI units of speed and velocity, we know that speed is independent of direction and velocity is speed specified with some direction. And continuing further, the rate of change of speed or velocity now will finally give us this parameter called acceleration. So, distance or displacement having the units SI unit as meter, and then rate of change of this will give us a parameter with unit meters per second, which is nothing but speed or velocity depending on the direction, and rate of change of this will give us a parameter with unit as meters per second square. So, this is where we have landed in the last lecture. We have discussed, we have stated what is acceleration, we have defined, we have seen the formula for acceleration, and then we have taken the SI unit of this. We have also worked out few numericals based on these parameters, and we have discussed the difference between vectors and scalars. The physical parameters which are dependent on direction are called vectors. So, any vector quantity, displacement, velocity, acceleration, all these things are vectors. Force you will be studying later. So, all these are vectors because they are direction dependent. And those parameters which are having only magnitude or the numerical value. So, we have seen magnitude of a physical quantity is nothing but the numerical value. So, those parameters which are concerned only with the magnitude, so these are called as scalars: distance, speed, time, temperature, etc. So, all these are called scalars. So, we have seen what is the difference between scalars and vectors, and though they differ in a way of the way of specifying the direction, the similarity is they are having the same unit. So, these two parameters will have the same units, these two parameters will have the same units, and so on. And we have also seen the difference between uniform and non-uniform motion. So, whenever an object covers equal distances and equal intervals of time, so we get this uniform motion, and unequal distances and equal intervals of time or equal distances and unequal intervals of time, we get non-uniform motion. Now, we come to an important point where we will be relating all these parameters, we will be showing all the changes in the form of a graph. So, let us see how it looks. So, introduction to graphs. So, all of you would have seen a graph paper. We know we have plotted some of the graphs in the earlier classes. So, basic examples, there are like two axes. One is the x-axis which you are familiar with, another is the y-axis. So, here a set of data points are given. So, x is having 3 different values 0, 1 and 2, and the corresponding y values are 4, 3 and 2. Suppose we plot these two on a graph paper, this is how the graph would look. So, the horizontal axis is called the x-axis, the vertical axis is called the y-axis, and the point of intersection of these two x-axis and y-axis is called the origin. So, this is what we would have seen in our lower classes. Okay, let us see. So, we have these two perpendicular axes which are called the x-axis and the y-axis. So, the horizontal one is the values when they change horizontally along this axis, we call it x-axis, and the other one is called the y-axis. Both are perpendicular to each other. Until now we have seen, so there are various x points for us now, how the x values keep changing and how the corresponding y values keep changing. So, based on, so we plot the points. For example, 4 points I have plotted like this, and my graph will look like this. So, I join all my points roughly. So, this is how a straight line graph it looks. So, if you connect all of them carefully with a scale, we can observe that this is a straight line graph. Some other graphs will be there. So, points variation will be like this. So, if you connect them, now these points cannot be connected by scale. So, through freehand when we connect, we see that this graph, this particular graph varies like this, and there is an equation associated with this graph. So, as the values keep changing, when we plot we will come to know how the nature of the graph will look. So, let us see now. So, you have seen, so the 3 different x points are there and the corresponding y values are given. So, when I plot I get like this. So, along the horizontal or x axis I have 3 points 0, 1 and 2. Along the y axis I have 3 different values, and for x is equal to 0 the y value is 4. So, that is how we get the first point, x is 1, y is 3, x is 2, y is also 2, and when I join all the 3 points we get the straight line. So, let us see, graphs provide a convenient method to present the basic information. So, now what we are dealing with? We are dealing with distances and displacements. So, therefore, distances, displacements or the speeds or velocities, so how they change with respect to time, we are going to use these graphs. Next one, to describe the motion of an object we use line graph. So, we know various kinds of graphs are there. So, we choose line graph to denote how the distances are changing with respect to time or how velocities are changing with respect to time. The third point, the change in position of an object with time can be represented on the distance time graph. So, distance time graph is one particular convenient method, a line graph method which is used to denote how change in distance happens as the time progresses. And similarly, variation in velocity of an object with respect to time is shown on velocity time graph. So, what happens here? So, one of the parameters is put on the x axis and one parameter is put on the other one is put on the y axis. So, how do we choose? We choose distance on the y axis and time on the x axis. Let us see why do we do that now. So, whenever we plot distance time graphs, this is how we choose the distance and this is how we choose time. Time is chosen on the x axis, along the x axis, because this is an independent variable. Time does not depend on anything, but how distance changes with respect to time. So, the tabular column could look like this, time and distance. So, if time is 1 second, after 2 seconds, 3 seconds, 4 seconds and so on, how will the distance keep varying? So, this is how we will be checking or representing the distance time graphs. So, time is independent. So, whatever is the independent variable, we plot it or we position it along the x axis. Whichever is the dependent variable, we keep it along the y axis, because distance depends on time. In the previous example, y depends on x. So, whenever you have plotted we have seen that we take x values, we fill up random x values independently, and dependent y, how that y will be for this particular x chosen. Similarly, time keeps changing, it is an independent variable. Whatever is independent variable, we place it along the x axis. The dependent distance will be on the y axis, and we keep seeing. So, in one particular numerical, the dependence is in one way, some other way. So, now we keep plotting. So, I get 3 different points. My points could be like this. So, I will get one nature of the graph. Suppose my points are different. Suppose I get points like this. This we have to explain. What does this mean? Or suppose I get my points like this. All the 3 points parallel to the time axis. I should be able to explain what is this and so on. So, let us see the distance time graphs. So, look at this now. The top right figure you observe. So, it is one example of distance time graph, and then if you are able to make out, this is something like uniform motion. The top right graph that you are observing, yeah, this one, it is the uniform motion. Why? As much the time is changing constantly, the distance also changes by equal amounts. So, between 0 and 1, in 1 second the distance changed to 10 meters, the next second it changed by 10 meters again, it reached 20. In the next second, that is for every 1 second there is equal change of distance. So, equal distances in equal intervals of time. So, straight away we know that now this is a uniform motion. So, this graph denotes uniform motion. The distance time graph where the line graph is at 45 degrees to the distance and time axis. So, a straight line graph like this will be denoting a uniform motion. So, let us start, let's look at the first graph now. Distance is along the y axis, time along the x axis. Distance is parallel to the time. The graph is parallel to time. So, what could this mean? If you think carefully, for various different values of time, if you see, the distance is not changing at all. So, let us see now. Let us look at this now. The graph is shown like this. So, time, let us say for example 1, 2, 3, 0, 1, 2, 3. So, the time is changing continuously along this axis, and my distance at 0, whatever distance value was there, at 1 second also the value did not change, at 2 seconds also the value did not change, at 3 seconds and so on. So, as my time keeps on increasing, so as the time progresses, there is no change in the distance at all, because distance either it should go up or come down. Let us see how it goes. It is not at all moving. The graph clearly tells that for whichever time I check, at 4 seconds or later say 100 seconds also, the graph is a straight line. There is no variation along the y axis or the distance axis. So, what could this mean? This only means that at any time there is no change in the distance travelled by the object, means the object is not moving at all, which means the body is at rest. So, this particular graph, this particular distance time graph where the graph line is parallel to the time axis is denoting body at rest. Why is at rest? Because at any time you see there is no change in the distance. If change in distance is not there, change in distance is 0. So, let us say for example this is 10 meters. So, at 0 seconds also when the time started it is at 10 meters, after 3 seconds also 10 meters only. So, change in distance is 0. So, therefore, body is not moving, it is at rest. Let us look at the next picture. Look at this now. We are having distance and time axis, and the graph is a straight line which is inclined at 45 degrees to both distance and time axis. And just now we have seen that this particular graph will denote uniform motion. Why? As much change in time is there, so equal changes in time intervals will correspond to equal changes in the distance. So, we have seen the top right graph there, this graph. So, what do we observe? For every 1 second change in time, the distance changes exactly by 10 meters. So, it is uniform motion. So, we know what does this graph denote. Now, look at this. This graph, the distance and time, as the time progresses, the distance is changing constantly, it is increasing, it is not increasing uniformly. For example, in the first graph that we see, the topmost graph, the top right graph there, we see the distance is increasing uniformly. In the third case, this particular case when we have seen, distance is increasing non-uniformly. Means what? Time is changing maybe by 1 second regularly, we are seeing the change in time by 1 second regularly, but distance is not changing uniformly, it is increasing in some other way. So, the graph looks like this, so uniformly increasing. So, let us see, the first one is body at rest, second one body moving with uniform speed, uniform or constant speed, non-uniform or non-uniformly increasing speed. So, the first picture denotes body at rest, body with constant velocity, the second one body with increasing velocity, the velocity is increasing. In the second case, the body is having constant velocity. In the third case, the body is having increasing velocity. So, these two, why is it constant? Because equal changes, the ratios are giving a constant value. The ratio of distance by time for any interval that we see in the second case is giving a constant number for us now. So, though the distance is changing, time is changing, but their ratio is constant. But in the third case, it is not so. So, let us see now, how do we justify that? So, average speed or average velocity, whatever we talk of, is nothing but change in distance by change in time. Now, if there is increase in distance and there is increase in time such that this ratio when calculated will give a constant value, then I get this number a constant, it does not change at all. Now, in the third case when we called it non-uniformly increasing speed, what do we mean? There is change in distance, there is change in time, but every time when I calculate the ratio of change in distance by change in time for every interval. So, between 1 and 2 seconds I calculate change in distance, I get the ratio as one particular value, I call it say, so case 3 I am talking of now. So, in case 3, the change in distance by change in time I calculated, I got the value speed 1 or V1 I call it. The next interval between 2 and 3 seconds, when I calculate the change in distance by time, it is V2, V3 and so on. Now, all these 3 values, they are not uniform unlike here. So, this is case 2 where the ratio is giving me a constant value. So, then I call it body moving with constant speed or constant velocity because the ratio is constant. But unlike this, in the third case, my values, these values are not constant, these values are constantly increasing. So, this ratio is giving some value here, in the next value is greater than this. So, V1 less than, V2 less than, V3 so on, they are not equal, they are constantly increasing. So, therefore, body moving with increasing speed. So, this is how we analyze. So, these are the 3 basic graphs in distance and time. So, let us see the graphs, VT graphs now. So, let us see how do velocity time graphs look. Now, look at this, the graph looks similar to those discussed in the distance time graphs. So, the first graph of d and t, distance and time, and this first graph, they are looking very similar, but the meaning conveyed could be different. Let us try to analyze now. So, I am having a velocity time graph. Velocity is placed along the y axis because it is dependent on time, how velocity changes with respect to time, but time is independent, time keeps changing. So, time is the independent variable, we place it along the x axis, velocity is the dependent variable, we place it along the y axis. Now, the first graph is like this now. Now, what could this mean? At any time 1, 2, 3, 4 seconds, the body is maintaining the same value. So, this is the velocity axis. Let us say the velocity, this point corresponds to 30 meters per second. So, 10, 20, 30. So, this third point will be 30 meters per second. So, initially the body is found to have the same velocity or same speed. As the time progresses, after 1 second also the body is maintaining the same speed, at third second same, fourth second same, and so on. So, this graph corresponds to body moving with constant velocity. Body moving with constant velocity. Why? The velocity value is not changing, it is neither going up nor down, it is maintaining at the same level, constant velocity. Now, the same graph, if you want to show in terms of distance and time, we have just seen for distance and time graph, body moving with constant velocity will be shown like this. So, suppose you are asked to draw a body moving with constant velocity in distance and time graph, you have to draw it like this. Body moving with constant velocity in velocity time graph will look like this now, because the parameters are changing along the y axis. If it is distance, I should know how to represent the graph moving with constant velocity or uniform velocity. If it is a different axis now, instead of distance I keep velocity here on the y axis. So, now I should know how the graph should look. So, just because both will denote body moving with constant velocity, here I should know how my graph nature will be, here how the graph nature will be. Okay. So, let us see the next one. So, the first case is done. Second case, velocity and time, it is a graph which is inclined at 45 degrees to the velocity time axis. Now, what could this denote? So, this is something uniform. So, in the last slide we have seen any straight line graph inclined at 45 degrees is uniform. Let us see what could be uniform in this now. So, we are seeing the velocity is changing, no doubt, the time is also changing, no doubt, but there is something more that is being conveyed. So, let us see now. So, how do we define acceleration? We define acceleration as change in velocity divided by change in time. Acceleration is change in velocity by change in time. Now, time kept on changing, 0, 1, 2, 3, 4 and so on. So, for any 2 points in the time, if we see, the change is 1 second. So, between 0 and 1, 1 and 2, 2 and 3, so on, time is changing 1 second. Now, if the velocity is changing in such a way that for every 1 second change in time, the velocity is changing by a fixed quantity, say 10 meters per second. Now, we know that when I take the ratio in every case, I get the ratio as A1 or A and so on, some value A. Why? Because change in velocity. So, suppose my time is time axis and velocity axis. I have 0, 1, 2, 3, 4 and so on. Here 10, 20, 30, 40, 50 and so on. Now, between any 2 intervals, so between 0 and 1, the change in time is 1 second, here change is 10 meters per second. So, velocity by time will give me what? Change 10 by 1, that is 10 I get here now. So, between these two I get 10. Between these two the change is 10, the change is 1. Change is 10, change is 1. So, is the case here. So if I take the ratio change in velocity by time 10 by 1, 10 by 1, I always get a constant value. I call it A, or let me call it now 10 directly, because we have taken this example 10. So velocity is increasing, time is also increasing, but the change in which this velocity is happening in a given time, the ratio is remaining constant. So this particular graph that we have seen in the second case, velocity and time graph, where the graph is looking parallel or not parallel, it is at a angle of 45 degrees to the velocity and time axis. So this particular graph will denote body moving with constant acceleration. Why? I get constant acceleration, velocity by time. Check the units, meters per second divided by second, it will be meters per second square. So a body is moving with constant acceleration is denoted like this. Now let me take the third case. Let me take this now. I will go to the third case and let us have a look at the graph. It is looking like this, velocity time graph, and the graph is looking curved. So how could the values be? So if you are observing the graph carefully, we know that as time increases, velocity values are also increasing, but not in a uniform way. So let us see how it will be. For example, if I have 10, 40, 90, 180 and 300 for example. So for every 1 second, so in the first 1 second, the body changed its velocity from 10 to 40, that is 30 meters per second change is observed. So what could be? So this is the case 2 is done now, case 2. So this is case 2. Let us come to case 3. So in the first interval, the ratio of velocity and time in the first interval will be 30 by 1. It is 30. Now what is the difference here in the second interval? So though my time is changing uniformly, velocity from 40 to 90 it is 50, 90 to 180 it is 90, 180 to 300 it is 120. Now look at this. This is how my ratios are looking. Change in velocity by time in the first interval 30 by 1, next 50 by 1, 90 by 1, 120 by 1. Now these values, the ratios, unlike here we have got a constant value 10, but here I am having 30, 50, 90, 120 and so on. So my ratios are not constant, but they are constantly increasing. It is not constant, it is increasing. So therefore this shows, and what does this ratio denote? Meters per second square, 50 meters per second square. So body with increasing acceleration, this is how my graph will look. And we have seen that the graph is like this, velocity, time, body with increasing acceleration. No doubt these changes are happening. Here also velocity is changing, it is increasing, time is increasing, but the ratio is constant. Here also velocity is changing, time is changing, both are increasing, but the ratio is not constant, it is increasing. So body having increasing acceleration or moving with increased acceleration. So it is an accelerated motion, this graph. So have a look at all the three graphs now. Body with constant velocity, the first one. Body with uniformly increasing velocity means constant acceleration. Velocity is changing, how? Uniformly. Time is also changing uniformly, so the ratio is constant now. Body with uniformly increasing velocity, or we can simply tell that body with constant acceleration. Body with non-uniformly increasing, why 30, 50, 90 and 120? It is non-uniform, while in the previous case it is 10, 10, 10, 10 so on. So therefore body with uniformly increasing velocity, or we can call the second case as body with constant acceleration, the third case as body with increasing acceleration. So this is how our graphs will look. Now can I have any other graphs, or is there any violation in drawing? For example, look at this distance and time graph. This graph though it looks somewhat okay, this is not fine, because look at the way in which it is drawn. First there is distance and time, the graph is at a 45-degree angle inclination, and then what happened, as time increased, what is happening, distance is reducing. So this, and from there it is increasing. So therefore as time increases, there is no reduction in the distance day to day life. So this graph is not valid. Similarly, for example, if we have a look here, so have a look at this graph. It shows the variation of distance with respect to time, and if you see carefully, if you observe carefully, we see that there is a gradual increase. The initial part of the graph is at an inclination of 45 degrees, and then we see that there is a bend in the graph, and then it increases again. If you observe carefully, there is a reduction or reversal in time, which is a violation. So time increases constantly. So as the time progresses, there cannot be a bend, or we cannot go back in time. So we have come to the point of say 5 seconds, and then we cannot trace back to anything lesser than 5. Time should constantly increase. So these kind of graphs, they are not valid, or these are not possible. Similarly, if you have a look here, we see that distance and time, and this time my graph is parallel to the distance axis. Means what? Suppose I give the value 0, 1, 2, 3, 4, 5, and then here I give 10, 20 and 30. This kind of graph, let us try to analyze. So at 3 seconds, as per the graph, the body is covering 10 meters also, 20 meters, 30 meters. So at a single time, without change in time, at a single time, the graph cannot shoot up. Why? There cannot be multiple distances at a single time frame. So in this particular time at 3 seconds, when we see that the distances are abruptly changing. So therefore this kind of graph is not possible. So whenever we try to analyze any given graph, we have to see how the change is happening with respect to time, with respect to distance, and then some more graphs will be there. So as you keep solving, some of the numericals will be taking up as to which all kinds of graphs these are not valid or which are not possible. So let us continue. So equations of motion. So now that we have studied a bit on graphs, so we will try to relate the different parameters that we have studied in graphical method. So using graphs, we are going to set up equations of motion. So how each parameter is related to another parameter. So have a look at this. For example, when an object moves along a straight line with uniform acceleration. So in this particular chapter, we are only dealing with objects with uniform acceleration, means constant acceleration. The accelerations are not changing. We assume that bodies are moving with constant acceleration. So when body moves with constant acceleration, so how the velocities will change, how much distance is covered. So all these parameters will be trying to relate them with different equations. So whenever an object moves along a straight line with constant or uniform acceleration, it is possible to relate velocity acceleration during its motion and the distance covered by it in a certain time interval by a set of equations known as the equations of motion. So the derivation for these equations of motion will be taking up in this particular lecture. So there are 3 such equations. The first one is v is equal to u plus at. V, the final velocity is, v denotes the final velocity, u denotes the initial velocity, s denotes the distance travelled, a denotes the acceleration, which is the constant acceleration of the body, and t denotes how the time is changing. So of the 3 equations, the first equation goes thus: v is equal to u plus at. The second one, s is equal to ut plus half at square. The distance covered is product of initial velocity and time plus half times acceleration into square of time. The third one, v square, the square of final velocity minus the square of initial velocity equals 2as, that is twice the acceleration multiplied by the distance. So let us see, let us take this velocity time graph, and the nature of the graph is a straight line. Now we know, once the nature of a velocity time graph is a straight line, we know that the acceleration is constant. The change in velocity by change in time always will give me a constant value. So therefore we say that the acceleration is constant. So let us take the first equation, the equation for velocity and time relation. Consider the velocity time graph an object that moves under uniform acceleration as shown. So this graph is there in your textbook, you can have a look at the graph. From the graph we will be able to make out that the initial velocity, so along the velocity axis, the initial velocity of the object is denoted by u at the point A, and the final velocity is denoted as v, small v at the point B. So the object started from A, it went to point B. So the velocity at A, I call it initial velocity u. So after reaching the point B, whatever velocity it is having, the velocity is v. So the change happened in a time interval t. So in the time interval between O and C, which is the t, the change happened. And we know that this change, the acceleration produced because of this change is a constant acceleration. Now look at the graph carefully, look at the points B and D. So the points, the length BD will give us the change in velocity from the point A to the point B. So initially at the origin the object is having initial velocity u, which means what? The length OA or the segment OA will denote the initial velocity u, and the segment OE will give us the final velocity. So let us try to draw the figure and then check in the graph. So let us see here. So this is the graph we have plotted. So the object is starting from point A and reaching point B. So it is a straight line motion, and then we know that the acceleration is constant. Now the initial velocity at this point is u, which means what? This segment OA will be u, and the final velocity. So these are the perpendiculars that I have drawn. So this is the extra construction that we need to do, so that we are able to relate to the parameters. So the perpendiculars are drawn from B to the velocity axis and the time axis, and this perpendicular AD is drawn from A to this segment BC. So this AD and OC, these are parallel. Similarly this length OE and the segment BC, these two are parallel. So along the velocity axis, initial velocity at point A is u. After reaching the point B, the final velocity is denoted by the segment OE. So OA is u and OE is nothing but v. But OA is similar as CD. Similarly, OE is similar as BC, because they are parallel. We have made the construction like that, and the change of time is denoted by OC, is taking the value t, which is nothing but AD. So remember these carefully. So from the graph we have listed out these. The segment OA and CD are equal to u, segment OE and BC are equal to v, the final velocity, and the segment OC and AD, these are equal to the time. Now let us see. So we drew parallels, we have seen what happened, and then finally we arrived at the conclusion that these segments are denoted by the parameters of u, v and t. Now, the acceleration of the object is given by change in velocity by change in time taken. So, let's from the graph we need to look at how the velocity is changing between which two points, and the time taken is denoted, the change in time is denoted between which two points. So, the acceleration is nothing but change in velocity by time. So, change in velocity is BD divided by change in time is AD. Okay. So, let us see change in velocity by change in time, which is BD. So, here. So, initially it was this, from here it became total is V. So, how much change took place? I need to know only this segment value, that is BD. So, acceleration is nothing but BD divided by AD. Why do we write this? Initial velocity is this, the final velocity. So, OA is the initial velocity, OE is the final velocity. How much change took place is this particular segment or this particular segment, both. So, this only this much will be the change. So, initially it was U, now the total is V. So, this will be V minus U, this is V minus U. So, BD will be V minus U divided by, what is the change in time, OC or AD? V minus U by change in time is denoted by small t. So, try to understand carefully, OA is the initial velocity, OE is the final velocity. Now, from A to B when the object underwent the journey, so the change alone from A to B is only this much. So, from total if I subtract this, I will get what is the segment value, which is V minus U, and here time is between 0 and t, I call it t seconds. So, finally I got A is equal to V minus U divided by t. If I cross multiply, V minus U is equal to A into t, or V is equal to U plus A t. That is, final velocity is equal to initial velocity plus acceleration into time. So, this is the first equation of motion which we have derived. So, in the next lecture we will be taking up the derivation of the second and third equation of motion and continue further with the chapter. Sai Ram and thank you.